All right, so today we're going to be talking about Thevenin and Norton equivalent circuits. So let's first talk about Thevenin's theorem. So Thevenin's theorem states that any two-terminal linear electrical network can be replaced by a voltage source VTH, standing for V Thevenin, in series with a resistance RTH. Okay. Here in a moment, I'm going to define what the rules are for what the voltage VTH will be and what the resistance RTH will be. But essentially, what Thevenin's theorem is saying here is that I can replace any two-terminal network with a practical voltage source, because a practical voltage source is literally just a voltage source in series with a resistance. Okay, so that's all we're doing today. And when we get to Norton's equivalent circuit here in a little bit, or Norton's theorem in a little bit, it'll be a current source representation. But all we're doing today is looking at an alternative way to do what we did in our last class meeting. I feel that this is much more powerful and more useful than just the simple source transformation approach and all of that kind of stuff. I want to make it very clear, you will not be explicitly tested on this material next Monday. This is the first part of the material for exam that will be on exam 2. That being said, there is remotely nothing stopping you from using this on exam 1 because it can make some things easier. So I am not going to explicitly ever ask you to do this on exam 1, but you can use it if you feel that it is appropriate for your problems related to source transformation, maximum power transfer theorem, and all of that kind of good stuff. Okay, so let's talk about what this Thevenin voltage and Thevenin resistance are, okay? So the Thevenin voltage, VTH, is the open circuit voltage measured across the terminals of the network slash component of interest. And the Thevenin resistance RTH is the equivalent resistance seen looking into the terminals of the dead network of interest. So let me talk a little bit here about a live network and a dead network, okay? So whenever we are determining our Thevenin voltage, we are going to be using a live network. All that means is that all of our independent sources, be they voltage sources or current sources, need to be on. So a normal circuit, okay? when we're determining the Thevenin resistance, we're looking at a dead network, and a dead network simply means that all of our independent sources are turned off. So when we calculate the Thevenin voltage, we want an electrically excited network. When we calculate the Thevenin resistance, we don't want to have any excitation messing things up, okay? So I'm going to give us a circuit here, and we are going to determine the Thevenin equivalent for this particular circuit, okay? So let's say that I have the following network. Let's make this 20 ohm resistor, an 18 ohm resistor, a 15 ohm resistor, and a 10 ohm resistor like so. And I want us to find the Thevenin equivalent circuit with respect to, or as seen by, the 10 ohm resistor, okay? So before we jump into this, there's two different cases of things that we're going to see whenever we're determining the Thevenin equivalent, and they're roughly going to boil down to the exact same process. So you might be asked to find the Thevenin equivalent circuit with respect to a particular element, or you might be asked to find the Thevenin equivalent circuit with respect to a pair of terminals, okay? As we'll see here in just a moment, they are literally going to boil down to the same thing. So whenever we're finding the Thevenin equivalent with respect to a particular circuit element, we have to take that circuit element out of the network, and that's going to leave us the open circuit terminals that we're going to measure the voltage drop across, or we're going to look into to see the equivalent resistance. So essentially, we take that element out because we don't want its presence influencing the measurements we are doing, okay? So here, because I'm asking you to find the Thevenin equivalent circuit with respect to the 10 ohm resistor, we will simply take this 10 ohm resistor out and then perform our analysis, okay? So let's start by finding our Thevenin voltage, okay? So I'm going to redraw this circuit really quickly. And I'm going to leave the 10 ohm resistor out of the circuit. And when I take it out of the circuit, it's going to leave behind an open circuit where it was. And I'm going to define my Thevenin voltage drop as the voltage drop across that open circuited set of terminals. Now, I arbitrarily chose the positive polarity terminal for this Thevenin voltage to be on top. Usually in your homework assignments and things like that, you will explicitly be told where to assume the positive polarity terminal to find your Thevenin voltage. And once we talk about Norton currents a little bit, you'll be told the reference direction for the Norton current. So this will not be guesswork for you all. For what it's worth, I chose the Thevenin voltage to be positive polarity on top and negative polarity on bottom in this case, because both of my other voltage sources are positive polarity on top, negative polarity on bottom. So I feel pretty confident that choosing this particular polarity for VTH is going to give me a positive number, okay? All right, so our ultimate goal here is literally to just use whatever method seems appropriate to find that voltage VTH. So what seems reasonable to you all? Sorry, what? Nodal analysis? Okay, that seems fairly reasonable to me as well. We are trying to find a voltage. This system doesn't have too many nodes, so nodal analysis it is. So just running through my steps of nodal analysis, the first thing I should do is identify all of my nodes. So here's one node. Here's another node. Here's a node. And here's a node. Which of these 4 nodes would we typically want to choose as ground? Blue one at the bottom, okay? I agree with that. Now I'm going to assign my nodal voltages. So this is going to be VA up top, VB over here, VC over here. I don't have any controlling variables to worry about, so I can skip that step. I do have 2 voltage sources, so I'll have 2 voltage relationship equations. So I'll have VA is equal to 18 volts and VB is equal to 5 volts. And if I'm not mistaken, the only thing that I have left to do for this particular system is then apply KCL at node C, because both my voltage sources are touching ground, so my supernodes will contain ground, and I won't have to write KCL equations at them. So KCL at C is going to look something like VC minus VA over 18 ohms plus VC minus VB over 15 ohms is equal to 0. And I'm now going to just solve this system for VA, which will obviously be 18 volts, VB, which will obviously be 5 volts, and then VC. I can't do that mental math in my head. All right, so I am lazy enough to literally put these 3 equations in as a system and just let it solve it that way. So in my first equation, my coefficient for VA is 1, my coefficient for VB is 0, my coefficient for VC is 0, my answer is 18 volts. In my second equation, my coefficient for VA is 0, VB is 1, VC is 0, constant is 5 volts. My third equation, my coefficient for VA is -1 over 18. My coefficient for VB is -1 over 15, and my coefficient for VC is 1 over 18 plus 1 over 15. And my constant term is 0. And if I type this into my calculator correctly, I got VC to be 120 over 11 volts. Did anybody else get that result? Yay or nay? Okay, getting a couple of thumbs up, so we'll move along from here. So now that I know those 3 nodal voltages, how would I find VTH? Exactly right. So we find it just like we would any other voltage in a nodal system. It's the nodal voltage at the positive polarity terminal minus the nodal voltage at the negative polarity terminal. Here, the nodal voltage at the positive polarity terminal is VC. The nodal voltage at the negative polarity terminal is ground. So great job. So VTH is literally just VC is 120 over 11 volts. Any questions, comments, or concerns about the analysis that we did here? All right. So the next thing that we're going to do is we're going to find RTH. So what I'm going to do now is I'm just going to redraw the circuit that I used to find VTH, except that I'm going to turn off all of my independent sources. So that means that my 18-volt source is going to look like a short circuit, my 5-volt source is going to look like a short circuit, and then everything else is going to stay exactly the same. And for what it's worth, we're not going to handle any circuits that contain dependent sources until Friday. So redrawing this guy, I have my short circuit replacing my 18-volt source. Here's my 20 ohm resistor. I have a short circuit replacing my 5-volt source. Here's an 18 ohm resistor. Here is a 15 ohm resistor. And these are the terminals that I'm looking into to solve for RTH. So I have a feeling that I know what this equivalent resistance is, but just to make sure I'm not going to make a mistake here, I'm going to identify my nodes and all of that kind of stuff just to be on the safe side. So here's one node. Here's my second node. So my feeling was correct, but I'll let you guys tell me what it is. What's the equivalent resistance we see here? What? Say that louder, please, Brendan. So the 18 and the 15 are in parallel. Absolutely right. The 20 ohm resistor is obviously shorted out since it's touching the same node on both sides, so it's not going to contribute anything. The 15 is between the red and the blue. The 18 is between the red and the blue, so it's just 15 in parallel with 18. Yes, sir. So whenever we're finding the Thevenin equivalent resistance, we need to be looking at a dead network, which means there is no excitation. So all of our sources, doesn't matter if it's an independent current source or an independent voltage source, we are going to turn them off when we look for RTH. Yes, Carter. We did instance that RTH was put in the same spot that VTH was? No, not at all. So let's go back to our definition up here. Okay. So the Thevenin voltage is the open circuit voltage measured across the terminals of the network. And the Thevenin resistance is the equivalent resistance seen looking into the terminals. So that you have to use the exact same terminals that you're finding VTH to find RTH. Otherwise, you're doing it wildly incorrectly. So must be the exact same set of terminals. So 15 in parallel with 18. And I'm just going to throw this into my calculator real quick. So I get 90 over 11 ohms. All right. So essentially what we have just determined is that this circuit right here, sorry, I can't remember the resistor values, 20, 18, 15, and 10. is electrically equivalent to this circuit. VTH was 120 over 11. RTH was 90 over 11. And here is our 10 ohm resistor. So we can replace that whole big ugly network with literally just that voltage source in series with that voltage source VTH in series with that resistance RTH, and our load, the 10 ohm resistor in this case, literally cannot tell the difference. So it will absorb the exact same amount of power, have the same voltage drop across it, have the same current flowing through it, et cetera, et cetera, et cetera. Okay. So the Thevenin equivalent circuit is just a different way to get towards being able to apply maximum power transfer theorem and all of that kind of stuff, instead of potentially doing multiple opportunities where you're doing source transformations back and forth and all of that kind of stuff like we did on Monday's class meeting. We just have a way to get directly to what practical voltage source is connected to my load resistance so that I can do these calculations. Brielle, how may I help you? So getting rid of which ones? So there isn't a 5 ohm resistor anywhere. So there's a 20 ohm resistor on the top left. There's an 18 ohm resistor on the top right. There's a 15 ohm resistor in the middle. Oh, the 20 ohm and the 5 volts. So okay. So this might be beating a dead horse, but I'm going to go back to the definition. Okay. So Thevenin's theorem says that we can replace any two-terminal linear electrical network by an electrically equivalent voltage source VTH in series with an electrically equivalent resistance RTH. Okay. So Thevenin's theorem, and as long as we follow these rules to calculate VTH and RTH, the whole point of this is to take this big network, which is connected to the 10 ohm resistor, and replace it with a voltage source in series with a resistor. To find VTH, we took our element out and we just used any method that we felt like to find that open circuit voltage. To find RTH, we looked at a dead network, so our voltage sources were turned off and found the Thevenin equivalent resistance. And then we're just using Thevenin's theorem to say, hey, now that I know what VTH is and RTH is, I can replace that whole network with that Thevenin equivalent. Just for shits and giggles, if you want me to, we can prove that they're electrically equivalent by determining the current flowing through the load resistor, determining the voltage drop across the load resistor in both cases, and see that they give us the same results. Would that help solidify things, or? Okay. So essentially, this is the process. If we are able to determine a Thevenin equivalent, and we believe through either faith or understanding, whichever way floats your boat is fine with me, that the Thevenin equivalent circuit is electrically equivalent, then we can simply replace that large network with the smaller one, which makes this circuit much easier to analyze. Okay, so this might seem like a silly question, but how would this process have been different if we were asked to find the Thevenin equivalent resistance with respect to a set of terminals instead of a particular component? We wouldn't have to take a circuit element out to start. That's literally the only difference. So if you're finding the Thevenin equivalent circuit with respect to a set of terminals, you already have the open circuit set of terminals to find the voltage across and to find the resistance looking into, so there's no need to do anything else. Okay. So now let's look at our Norton equivalent circuit real quick, or Norton's theorem. Okay. So Norton's theorem is almost exactly the same as Thevenin's theorem, except that it says that we can replace our circuit with an electrically equivalent practical current source. Okay, so any two-terminal linear electrical network can be replaced at the terminals by a current source, I Norton, in series, excuse me, in parallel, my apologies, with a resistance R Norton. Once again, since we learned on Monday that a practical current source is just an ideal current source in parallel with a resistance, Norton's theorem is essentially just saying, I can make any two-terminal network look like a practical current source. So let's talk about the rules for determining I Norton. Okay. So the Norton current I Norton is the short circuit current flowing between the two terminals of the live network, and the Norton resistance, sorry, that scrolled way too far on me, R Norton is the resistance seen looking into the terminals of the dead network. So essentially, the Norton resistance and the Thevenin resistance are literally the exact same thing. So I'm never going to call it Norton resistance again. I'm always just going to call it Thevenin resistance because that's what we learned first. Okay. So what I want to do now is I want to take that exact same circuit that we looked at a couple of minutes ago, and I want us to find the Norton equivalent circuit representation for that. So here's our circuit of interest. We are going to find the Norton equivalent circuit with respect to the 10 ohm resistor. And nope. Sorry. Oh, good God, stop. Stupid virus scan. All right. So essentially, how we're going to define our Norton current is going to be dependent on how we defined our Thevenin resistance. So I'm always going to choose to draw my Norton current as if it were flowing into the positive polarity terminal of how I defined my Thevenin resistance. So in that case, this is going to be direction down. Like I said previously, on your homeworks, on your exams, things like that, you will always be told what direction to assume anyway, but I'm just trying to make sure that you're aware of the rules in case you have to do this on your own without assistance, okay? So the only thing we're actually going to bother finding here is the Norton current because we already found the Norton resistance since we found the Thevenin resistance, okay? So I'm going to redraw my circuit. That should have been a 15 ohm right there. I take my 10 ohm resistor out. And because I'm finding the Norton current, I have to short circuit those terminals. And the Norton current is just the current that's flowing through that short circuit. So essentially, whenever I'm finding Thevenin resistance, I replace my component of interest, Thevenin voltage. I replace my component of interest with an open circuit and find the voltage drop across that open circuit. Whenever I'm finding the Norton current, I replace my component of interest with a short circuit, and I just find the current flowing through that short. So how do you guys suggest we might solve for this Norton current? Mesh. Seems perfectly reasonable. We're trying to find a current, okay? So let's call this guy mesh A, B, and C, like so. Good gracious. I don't know why my penmanship is so much worse today, or at least I feel it's so much worse today than it has been in previous class meetings. So mesh analysis. We don't have, we've already defined our meshes. We don't have any controlling variables. We don't have any current sources, so we don't have any super meshes. So it's literally just going to be 3 applications of Kirchhoff's voltage law. One around mesh A, one around mesh B, and one around mesh C. So somebody tell me what my KVL around mesh A is going to look like. So negative 18 volts plus 20 ohms IA minus IB plus 5 volts is equal to 0. Great job. Thank you. Somebody else tell me what my mesh B equation is going to look like. So 20 IB minus IA. $18 IB. All right. Great job, Brielle. Thank you. Somebody else tell me what's going on with mesh C. Negative 5 volts. IC minus IB. Okay. I disagree. Yeah, just equals 0. Absolutely right. So because we replaced that 10 ohm resistor with a short circuit, we are done. We started and ended at the same node. And so now we just need to solve this system. So I'm going to throw this in my calculator here in just a second, but I'm going to leave myself space. So here's IA, IB, and IC. So my coefficient for IA in my first equation is 20. My coefficient for IB in my first equation is negative 20. My coefficient for IC in my first equation is 0. And then my constant term is going to be 18 minus 5. In my second equation, my coefficient for IA is negative 20. My coefficient for IB is 20 plus 18 plus 15. My coefficient for IC is negative 15. and my constant term is 0. And in my third equation, my coefficient for IA is 0. My coefficient for IB is -15. My coefficient for IC is +15, and my constant term is +5 volts. So if I type this into my calculator correctly, I got 33 over 20 amps for IA, 1 amp for IB, and 4/3 of an amp for IC. I feel pretty strongly I got this right. And I'll explain how and why I feel really strongly about that in just a moment. But what would my Norton current be here now that I know these 3 mesh currents? So the same thing as IC. Okay. So 4/3 amps. So I Norton in this case is IC is 4/3 of an amp. Since we already found the Norton resistance, because again, it's the same thing as the Thevenin resistance, I can say that my original circuit, 18 volts connected to 20 ohm resistor, connected to a 5-volt source over here, 18, 15, and 10 is electrically equivalent to a 4/3 of an amp current source connected in parallel to a, if my memory serves me correctly, 90 over 11 ohm resistor connected in parallel to my 10 ohm load resistor, like so, where I've just replaced that big ugly network with the Norton equivalent, which is the current source in parallel, Norton current source in parallel with the Norton resistance. All right, so any questions on the analysis we did here or the substitution at the end, effectively just replacing the big ugly thing with the simplified Norton equivalent? All right, so I want to take us on a little bit of a logical journey here, okay? Won't take long. So up here, I said that this circuit, our original circuit, is electrically equivalent to VTH in series with RTH in series to the 10 ohm resistor. Down here, I said that our original circuit is electrically equivalent to our Norton current in parallel with our Norton resistance in parallel with our 10 ohm resistor. So if both of these circuits, the Norton equivalent circuit connected to the 10 ohm resistor and the Thevenin equivalent circuit connected to the 10 ohm resistor, are electrically equivalent to our original network, it stands to reason that they're electrically equivalent to each other as well, right? So essentially, what I'm implying is that 120 over 11 volts in series with 90 over 11 ohms in series with a 10 ohm resistor is electrically equivalent to 4/3 of an amp in parallel with a 90 over 11 ohm resistor in parallel with a 10 ohm resistor. Or put it in another way, the Norton equivalent circuit is just the source transformation of the Thevenin equivalent circuit and vice versa. So if I can find one, I can immediately find the other using the exact same relationships that we discussed in our last class meeting. So essentially what we have is our Thevenin voltage is equal to our Norton current times our Thevenin resistance or our Norton current could be expressed as our Thevenin voltage over our Thevenin resistance, or our Thevenin resistance could be expressed as our Thevenin voltage over our Norton current. So essentially, if we can find all three of those quantities, we have a way to check our work, right? So if I can find my Thevenin voltage by measuring the open circuit voltage across the terminals, and then I find my Thevenin resistance by looking at the resistance of the dead network, and then I find my Norton current by determining the short circuit current. If these relationships are true, I must have done everything right. If one of them is off, well, I don't know where my mistake was, but I know that I've made a mistake somewhere. So let's test things just real quick, right? So our Norton current is 4/3 of an amp. Our Thevenin resistance is 90/11ths of an ohm. When I multiply those two guys together, 4/3 of 90 is 120. So I should wind up getting 120 over 11 volts. You can throw that into your calculator if you feel like it. And if that's true, it proves that we did everything correct. All right. So I've only ranted about Thevenin and Norton equivalent circuits for 45 minutes. So let's work another problem. So let's say that I have a 7-volt source. Here's a 10 ohm resistor. Here's a 5 ohm resistor. A 12 ohm resistor. Two amp source like so. And let's make this guy a 15 ohm resistor. And I'm going to give myself a set of terminals out here on the right that I'm going to call A and B. And my goal here is to find the Thevenin and Norton equivalent circuits with respect to terminals A and B. And I'm going to say explicitly plus of VTH is on top and I Norton is going to be measured down. So which of these three quantities do you guys want to solve for first? The Thevenin resistance, the Thevenin voltage, or the Norton current? Thevenin voltage, okay? So redrawing my circuit. Here's the Thevenin voltage that I'm looking for. what analysis technique would you guys like to use? So we could use nodal. Let me think here. 1, 2, 3, 4 nodes total. One of them is going to be ground, so it's going to be a 3-equation, 3 unknown system. We're trying to solve for a voltage. We could, for what it's worth, also use mesh. It's going to be a 3-equation, 3 unknown system. But since mesh is going to give us currents, I would probably do nodal here just because it's equal difficulty either way, and because I'm trying to find a voltage and nodal gives me voltages directly, that's probably what I would do. So nodal analysis seems perfectly reasonable to me. I'm going to identify my nodes. Like so. Brian, which node do you want ground to be at? Okay. No dependent sources, so no controlling variables. I do have a voltage source. So actually, let me assign these nodal voltages before I forget about it. So let's call this guy A, B, and C. We could say that VA is going to be 7 volts. And now we would just need to apply KCL at node B and node C. So somebody tell me what my KCL at node B equation is going to look like. What was that? So VB minus VA over 10 ohms is my first term. Plus VB over 5 ohms, okay? Minus 2 amps, all right. Is equal to 0, okay. Now somebody tell me what my KCL equation at VC is going to look like. So VC minus VB over 12 ohms plus VC over 15 ohms is equal to 0, right? And now I'm just going to solve this system for VA, VB, and VC, and hopefully we can all see very easily that VC and VTH are going to be the same thing. So I'm literally just going to go ahead and write that in there. So throwing this into my system solver. My coefficient for VA in my first equation is 1, VB is 0, VC is 0, constant term is 7. And my second equation, my coefficient for VA is negative 1 over 10. For VB, it's 1 over 10 plus 1 over 5 plus 1 over 12. For VC, it's negative 1 over 12. And my constant term is 2 amps. And my third equation, my coefficient for VA is 0. For VB, it's negative 1 over 12. And for VC, it's 1 over 12 plus 1 over 15. Constant term is 0. When I solve this guy, I get VA is 7 volts. VB is 729 over 91. And VC is 405 over 91 volts, which will be VTH. Matthew, you look like you might have had a question. No, okay. So before we move on from here, does anybody have any questions, comments, or concerns? All right. What do you guys want to solve for next? Norton current or Thevenin resistance? Thevenin resistance, okay? So in this case, I'm just redrawing my circuit and I'm turning off my independent sources. So my 7-volt source is going to look like a short circuit. My 2-amp source is going to look like an open circuit, which means I'm just not going to bother drawing it. So essentially, I should have something that looks like this. So there's my short circuit for my 7-volt source. Here's my 10-ohm resistor. Here's my 5-ohm resistor. My 12-ohm resistor. My 15-ohm resistor. And I'm looking in through this set of open circuited terminals. I'm making that notation explicitly because some of you, and I tend to do this as well, might actually draw the terminals that are left behind by removing that current source. And this gets to Carter's question a little while ago. How do we know which set of terminals to find the Thevenin voltage across or find the Thevenin resistance? It's the same ones that we did earlier, right? So if we're finding it with respect to A and B, where this guy up here is A and this guy up here is B, then we have to find REQ with respect to A and B as well. Okay. So for this guy, I think we can probably figure out what's going on without fully identifying the nodes and all of that kind of stuff. So what are your thoughts on what this resistance is going to look like? So I heard somebody say 12 in series with 15, and I already disagree. For else. Work our way from left to right. Okay, so 10 in parallel with 5, in series with 12, and all of that is in parallel with 15. So I'm saying it is 15 ohms in parallel with 12 ohms plus the parallel combination of 10 ohms and 5 ohms. So that would mathematically look like 15 ohms times 12 ohms plus 10 ohms times 5 ohms over 10 ohms plus 5 ohms, all over 15 ohms plus 12 ohms plus 10 ohms times 5 ohms over 10 ohms plus 5 ohms. And throwing that into my calculator, that would look like, let's see, $690 over 91, or 7.582 for those of you that want a decimal. Any questions, comments, or concerns about how we found this Thevenin equivalent resistance? All right, so we could, if we were so inclined, find our Norton current by simply taking VTH over RTH. I'm going to use that as a check. So I want us to actually find what I Norton is, and then make sure that it comes out to be simply VTH over RTH to make sure that we did all of our steps correctly. Okay. So the last thing that we're going to do here is find I Norton. Okay. So just to recap, to find our Norton current, we're simply going to short circuit our terminals and then figure out how much current is flowing through that short. So we've got our 7-volt source. Here's our 10 ohm resistor. Our 5 ohm resistor. 12 ohm resistor. 15 ohm resistor. believe this was a 2 amp source blowing up and to the left. Here's terminal A, here's terminal B. I'm short circuiting my terminals, and my Norton current will be found direction down. So what analysis technique would you guys care to use here? Mesh, okay? So I would probably tend to use mesh as well, but I'm going to make a slight modification, okay? I feel like you're already catching what I'm throwing, but because the 15 ohm resistor is shorted out, we know that it's not going to contribute. So I'm literally going to cross these guys out, and I'm going to make this thing one of my meshes. So I'm just avoiding the 15 ohm resistor because I know that it's literally not going to contribute anything. So I'm going to call that guy mesh C. Over here, this will be mesh A. And down here in this little triangle, that'll be mesh B. Okay. So no controlling variables. I do have a current source. So what's my current relationship equation going to look like for this guy? 2 amps is equal to what? IC minus IB. Thank you, sir. Because that is an interior current source, I will have to write a super mesh equation containing meshes B and C. So somebody tell me what that's going to look like. So 5 ohms IB minus IA. Thank you, Caleb. You can keep going, or if you want somebody else to take over, that's cool too. 12 ohms times IC. Anything else? Nope. We started at the bottom node. We ended at the bottom node. We're good to go. So just equal 0. Okay. The only thing we have left is to write a KVL equation around mesh A. So somebody else tell me what's going on there. Nope. If we're writing a Kirchhoff's voltage law equation, we should never have a current source in it at all. So we're doing KVL around mesh A, and the 2 amp source isn't touching mesh A either. So care to take a crack at it again? We're doing mesh A. Minus 7 volts. Equals 0. Thank you, sir. So we already took care of everything that was going on in meshes B and C with that current relationship equation on top and the KVL around our super mesh in the middle. So the only thing that we had left was KVL around mesh A. We're now good. 3 equations, 3 unknowns. So let's solve this system. So we could say, let's see, IA is equal to something. IB is equal to something. And hopefully we can all see that IC is going to be I Norton. And that'll be equal. That looks too much like a 10. So I'm going to throw this into my calculator. So in my first equation, my coefficient for IA is 0. My coefficient for IB is -1. My coefficient for IC is +1, and my constant term is 2 amps. In my second equation, my coefficient for IA is -5. My coefficient for IB is +5. My coefficient for IC is 12. My constant term is 0. In my third equation, my coefficient for IA is 10 plus 5. My coefficient for IB is -5. My coefficient for IC is 0. My constant term is +7. Solving this system, I got IA to be -1/230 amps. IB to be -65/46 amps. And IC to be +27/46 amps. So if I do I Norton is equal to VTH over RTH, that would be, sorry, I scrolled so far, 405/91. Divided by 690/91, which is just going to be the same as 405/690. So 405/690 is 27/46. So we must have done all three parts correctly.